All right, I think we're ready to start. So, welcome everyone. This is the second Security Club beginner workshop. Um, so today we're going to be going over a quick intro to networking. So just an overview of things we're going to be going over. We're going to be covering what protocols are, what layers are, encapsulation, and IP addresses and other stuff relating to IP. So at a most basic level, computers communicate by turning on and off a signal in some sort of wire, or sometimes like with Wi-Fi, it's a radio wave or something like that. But fundamentally, it's just like turning a signal on and off. So the question we want to answer is, how do computers interpret these signals and figure out what to do with them? So just like humans have languages, computers have protocols. So protocols describe how to encode and decode information, like what information to send in what order, stuff like that. So as an example, we have this protocol called HTTP. This is what's used for websites. Um, so messages for HTTP are sent as ASCII text following a specific format. It's kind of like a programming language. So this is a really simple example. It's just get slash index.html and then http slash 1.1. So it's a verb, which is usually get if you're using a web browser, then the path, and then the HTML version you're using. And other information can come after that too. There's a lot more that goes into HTTP. Most requests aren't going to be this simple, but so any questions about this so far? Yeah, so this is just an example. This is the protocol that's used for websites. And most requests are going to be a lot more complicated than this, but this is just to give you an idea of like what a protocol looks like. HTTP is a simpler one because it's all plain text. Most protocols are not text. They're like you send binary data, so you can't just like read them like this. Does that make sense? Any other questions? All right. So to send someone a message, you need to include who you're sending it to and where they should reply to. So it would be really tedious if every single protocol like HTTP had to handle this individually, because there are a lot of protocols for things like if you want to access a website, obviously, then there's like protocols for games, there's protocols for like file transfer, everything like that. So the solution is we use multiple protocols sort of layered together. So the internet protocol handles identifying the sender and receiver with IP addresses. That's what those are for. And HTTP only has to handle the actual messages that are getting sent. So basically, we split up the responsibilities into separate protocols so that we only have one protocol that actually needs to deal with getting a message from point A to point B, and all of the other ones can just deal with what's in the message. So the new problem is, what do we mean when we say we're using multiple protocols? So most lower level protocols, like the internet protocol, have some kind of header followed by arbitrary data. And that data can be like literally anything. So essentially, most protocols are just containers for other data. So a very simple version of IP could just have the source IP address, the destination IP address, and some data. And the real IP has a lot more than that, but it's not really important for now. So the key idea is that the data we put inside one of these packets could be a message for another protocol. So as an analogy, you can think about a package. If you ship the package with USPS, you get a box, you put something in it, you label it, and you drop it off at a post office, right? But they're not going to open up your package to look what's in it, usually, most of the time, unless you're on like a terrorist watch list or something. uh,
Same goes for the internet too.
that's true, yeah. So they don't really care what's in the box aside from like how big it is, how heavy it is. All they're gonna look at is look at the label and figure out where it should go. So the idea is you could, in theory, just put another box inside there, and the USPS wouldn't know the difference, right? Because they're only looking at the outermost box. But then whenever someone gets the box, they'll open it up and they'll see the inner box, and they'll hopefully have some idea of what to do with it, whether they should like open it up or maybe it needs to be sent somewhere else if it's going to like a big warehouse or something. So it's sort of the same idea as putting an HTTP message inside an IP message. You're taking two protocols and combining them in that way. Does that make sense? Any questions?
The key thing about that is you have all the information. So, like for example, think of it as like the shipping label on each part of the box, or like the address or a note. Each of those has information only for that level. So, for example, the outer shipping label could be for USPS to basically get your package where it needs to go. And then inside could be, for example, present. And then that has the note to you from the person saying that. So, for example, that could be, in this case, that could be the HTTP data.
Right, yeah. So as a simplified example, this is what it could look like when we combine these two things. So first we have our IP header where we have the source address, the destination address. These are just random example values. And then we have data at the bottom. And then after that data, we just have an HTTP request. So it's sort of like we put the HTTP request inside an IP packet. Does that make sense? This isn't what it actually looks like, just to be clear. This is just an example of what it could look like if it was a lot simpler. So protocols are split into categories called layers, and each layer has a different responsibility. So just like we said, the internet protocol's responsibility is getting stuff where it needs to go, and HTTP is just there for like requesting website contents and then sending those contents back. So it's actually split up into a few more layers than that. It's not just two. So there are two major stacks. I think there's a few names for it. They're also called like models. They're different ways of splitting up the layers, basically. So they're called OSI, which is Open Systems Interconnection, and TCP/IP. So TCP/IP is the simpler one. OSI is what most people use for networking terminology. Um, it's sort of weird, so just show on the next slide. So TCP/IP has protocols split into 4 different layers, and OSI has them split into 7. So basically, the transport layer is the same. We have network on the right and internet on the left. They're basically exactly the same. And then the important parts are that in OSI, you have these session and presentation layers. And in TCP/IP, there's just an application layer that encompasses everything. And then also OSI splits network access into 2 sections called data link and physical. So the way this works is really weird because most terminology we use for networking comes from the OSI model, but it's sort of like the TCP/IP model is more it's more closer aligned to what we actually use in the real world. So I think this is easier to show with the diagram. The presentation and session layers, no one ever says anything about those. No one's ever going to mention them. They don't really matter at all. So like for all intents and purposes, the application layer is basically the same across both. But since the application layer is the top one in OSI, we call it layer 7, even though like functionally the presentation and session layers don't really exist. And then sort of similar thing with the data link and physical one. Usually there's not much of a distinction between these two. They're basically just treated the same thing. But usually if you're talking about a protocol down here, you'll just call it layer 2. So yeah, that's basically that. Does anyone have any questions about it? All right. All right, sure.
So these are actually, if you, so going back to the OSI model, we're going to talk about the data link and the physical layers first. These are the 2 lowest. In this case, they're equivalent to the TCP/IP, the network access layer. So this is basically what's going on under the hood on the network. So the physical layer describes how the signals are physically transmitted. So that could be, for example, the Wi-Fi card in your laptop. That could be the physical layer actually sending the radio signals. Could be a copper wire actually carrying physical electrical signals. Could be a fiber optic cable with carrying light across continents. All of those are the physical representation of the data. It's usually lumped together with the data link layer because in order to have the physical layer mean anything, the data link layer has to then take that information and establish a connection. So the data link layer then describes those low-level details, which are being sent between computers across a local area network, also known as a LAN. In this case, what we experience for these layers, the most common ones are Ethernet, so that would be the physical wires like copper cable in your house, and Wi-Fi, which is what most of you are using to access the internet right now. And they both work similarly at a high level. So like we're going back to the encapsulation idea, all of the data is being transmitted over the internet, over that or over that local connection. And for example, the application layer doesn't really care about how it's being transmitted. The website doesn't care that it's being sent over a copper wire versus a Wi-Fi signal. It just cares that it gets to its intended recipient. But at the physical and data link layers, they only care about how it's being transmitted and where it's being transmitted to. They don't really care about what data is being sent. So that's really the encapsulation idea in practice. Good so far? Nice. So in this case, the MAC addresses, they're typically done at the data link layer. This is part of the Ethernet standard and Wi-Fi. They're globally unique addresses, and each of your network interfaces gets its own MAC address. You can change your MAC address. You can spoof it, but it's not really necessary for connecting to the internet. That's more done for other reasons. Each of them, they're 6 bytes long, and they're written in hexadecimal, which is just a way of representing numbers. So we use the base 10 system, 0 through 9, binary 0 and 1, hexadecimal 0 through 9, and then A through F, so 0 to 15. So in this case, you can see it's AA, BB, CC, DD, EE, FF. So each of those bytes is separated by a colon, and they're used to physically identify who is the receiver and receiver, because we don't really care about at the data link layer and the physical layer. We don't really care about kind of where on the network you're located. We just care about where the physical signals are being sent to. Good so far? As part of the MAC address, you have your organizationally unique identifiers. So these are the first 3 bytes. So in the previous example, that would be your AA, BB, CC. So that would be your the organizationally unique identifier. What those do is they're actually assigned to companies by an organization called IEEE. They're a governing body for a lot of electronics, hardware, networking equipment. They're a professional and standards organization as well. Each company is free to use any MAC address, but their first 3 bytes have to start with their OUI. So for example, a popular wireless manufacturer is Realtek. They would get their OUI, and then any of their devices could essentially have their own serial number identifier as the last 3 bytes. And you can look up the OUI for the MAC address to figure out the manufacturer. So for example, if you get a MAC address, you can look at those first 3 bytes. And if the MAC address isn't spoofed, if it isn't changed, you can see, oh, this is a Realtek chip. This is a gigabyte network card, for example, stuff like that. And the MAC address only really identifies the actual physical hardware being connected. So for example, let's say you have a network card in your computer and your friend has a different network card in their computer. If it's the same chip, it's going to have similar MAC addresses. They'll be different, but they'll be similar.
Yeah, sure. So this is the layer we talked about earlier called IP, the Internet Protocol. And this is the layer that essentially defines the Internet, as you might guess from the name. So it's necessary to send messages between computers on different local area networks. And in theory, you could technically just use layer 2 Ethernet and Wi-Fi to send messages to each other on layer 2, but no one does this because it would be really inconvenient to switch between like not using the internet protocol and using the internet protocol, depending on whether you're talking over the same local network or you're talking to someone on the other side of the world. So there are two big versions of the Internet Protocol. There's IPv4 and IPv6. IPv4 is the much more widely used version. If you've ever seen an IP address, it's almost definitely an IPv4 address. IPv6 is very slowly replacing it. It's been around for like almost 30 years, I think, at this point, but it's been people have been very slow at adopting it, so it's still like not even close to IPv4.
Most people consider IPv6 kind of harder to use in a way, just because it's longer. It's not as nice looking as IPv4. It's easier to learn IPv4 too, and it's an older standard, so more equipment is equipped with IPv4.
It's not even older by that much, though. It's only like a few years, which is pretty funny. So, just a side note about IPv6 adoption. A lot of people say that no one uses IPv6, but it's not really entirely true. So, this is Google's chart on how many people access their website with IPv6. And you can see, like, in the current day, it's getting to like 45%. So, like, almost half of people who use Google are using it over IPv6 at this point. One of the reasons for that is we'll get to in a second. IPv4 addresses, there aren't that many of them, so we're sort of running out. So most cell networks actually use IPv6. So like if you're on mobile data, there's a pretty high chance you're using IPv6 instead of v4. So an IPv4 address is a 32-bit number that identifies a specific computer on a network. We usually write an IP address with each byte as a single number in decimal separated by dots, and this is called decimal dot notation. So, for example, 192.168.1.1 corresponds to a 32-bit number where the first byte is 192, the second byte is 168, and the last two are both 1. Does that make any sense? Does that make sense? Any questions? Okay. So IPv6 addresses. So these are basically created because IPv4 was running out of addresses because 32 bits is only 4 billion addresses, which is not really a lot when the internet covers the entire world because there are twice as many people as IP addresses at this point. And then people have like multiple devices and stuff like that. So um, IPv6 addresses are 128 bits, so it's 4 times as many bits, which since adding another bit doubles the amount of addresses, this is like the amount of addresses for IPv4 to the fourth power. So it's basically infinite for all practical purposes. So these are formatted differently because if you wrote this in decimal dot notation, it would be really long. Yep. What do you mean?
Yeah, it's not so like each machine will not like each machine is not guaranteed to have its own unique IP address. On a given network, it will. But like for example, if your machine was connected to one network and your machine was connected to another network and they both used the same subnet and different numbering, we'll get to that. But
Yeah.
like for your machine could have the same IP address. They're not unique. Yeah, on a network, they're used at the network level, not at like the physical level.
We'll get to that soon. Uh, so So yeah, there's some formatting rules to make these shorter. At the bottom, this is an example of a completely unabbreviated IPv6 address, and it's massive. Uh, and just for scale, just these last 8 digits alone would be an entire IPv4 address. So IPv6 addresses are huge. Um, but there's some rules for abbreviating it. So within a single within a single group of 4 digits, you can leave out leading zeros. So for example, you can write 5AB instead of 05AB, and you can abbreviate multiple zeros in a row with a double colon. So for example, we could abbreviate this whole thing as just 123 double colon AB, which is much shorter. Yep.
default, I guess. Is that
Right.
the same for IPv6? Like, you can have like the same ones on like a private network.
Yeah, so that's something we'll mention briefly later, but with IPv6, the idea is you have so many IP addresses that you should never need to use the same IP twice, even on completely separate networks.
So on like default, they won't put it's like the same thing.
Right, yeah.
There's also a difference we haven't gotten to it yet, but there's also a difference between your private network and like the global networks or the internet. Um, it's a difference between a private IP and a public IP, and the reason that was implemented, I think, was because of the IPv4 to IPv6 changeover or like adaptation, because the private IPs could use IPv4, but you need IPv6 to be able to address every computer on the internet, because IPv4 just doesn't have that capability. There's too many.
Nice.
Yeah.
Any other questions? All right. So a network in the Internet Protocol is basically just a range of IP addresses with the common prefix. And just to be clear, for most of the rest of this presentation, we're just going to stick with IPv4 because it's more common and also shorter to write stuff out. So you can represent the length of the prefix for a network with the subnet mask, like 255.255.255.0. This is an example. We write this in decimal dot notation too. And each one in the binary version of the mask corresponds to a bit that all addresses in the network share, and each zero corresponds to a bit they don't share. So this would be basically 24 ones followed by 8 zeros. And just quick note about usable addresses on a network. The first and last addresses in any network are reserved. So the first address is called the network address. It's used if you want to refer to the network as a whole instead of a specific device. So this is mostly just to prevent it from being ambiguous. So like if you use the network address, it's clear that you're not referring to any specific device just when you're like talking about it or maybe inputting it into a program or something like that. And then the last address is the broadcast address. And then this is where you can send packets and your router should forward them to every single device on your network. And all other addresses are free to use. You can just assign them to any device. So going back to the subnet mask notation, we have this thing called CIDR notation or CIDR notation. It's just a shorter way of specifying the subnet mask. So this works because the first bits of the mask are always all ones, and then it changes to all zeros. So you can't have something like 101 in a subnet mask. It can't switch from 1 to 0 and then back to 1. So for example, in our example earlier with 255 to 255 to 255.0, the first 24 bits are all ones, and the last 8 bits are all zeros. So for CIDR notation, we just say the number of 1 bits. So here that mask just becomes a 24, and we write it after the IP address separated by a slash. So for example, we could write 192.168.10/24. That would mean we have a network containing this address, and the subnet mask would be this, basically. Yep.
What is the subnet mask used for?
So those over here, it's just used for saying what computers are on a network, basically. So anything that's a 1 in the subnet mask, that means every computer on this network shares that bit in their IP address, so it'll be the same. And anything that's a 0, it could be different depending on which computer in the network you're looking at. So there's an example on the next slide. This is an example of how you would interpret this. So 255 is all ones in binary. So the first 3 bytes are all ones, and the last byte is all zeros. So that's 24 ones and then 8 zeros. So what this means basically is that every device on this network or every address on this network shares the same first 3 bytes. So for example, if we know that 192.168.1.1 is on this network, then that means that 192.168.1.2 is also on this network because they share the first 3 bytes. But if we take 192.168.2.1, that would not be on the same network because the third byte is different.
Okay, and then where is the subnet mask used?
So the subnet mask would be used like when you configure your Wi-Fi setup, basically. So usually, most of the time, it's done automatically for most networks you connect to. So that's something we'll get into in the next workshop, how that protocol works. But if you wanted to put it in manually, if you've ever like gone into Windows settings and switched your internet configuration mode to manual, it'll ask you for IP address and subnet mask to put in. Yep.
Sorry, just another thing too is it's also very helpful for defining networks of different sizes. So for example, in this case, the network address itself is those first 3 bytes, but then all of the devices have to be within that, well, the 1 to 254 range in that last one. If I was to say have the subnet mask be 255.0.0.0, then the actual like range of the network address would only be that first byte, but then I could have a lot of devices on that one network.
Right.
Sorry. Yeah.
Yep. What did you say?
That was my question.
Okay.
Okay. Yeah.
You can interpret that as how many like end devices IP address you can have.
Yeah.
Right?
Yeah, and it's pretty common to use the CIDR version. So just for example, this would be just /24 because there's 24 1 bits. So it's common to use that to specify how big a network is. So like if someone says like their network size is /8, that basically means that just like he said, you have a subnet mask of 255.0.0.0, which means that you have space for all 3 of the last bytes to be changed.
Doesn't mean like /24 doesn't mean IPs.
Right, yeah. It basically means like there's 24 bits that all of the IP addresses in this network share. So a smaller CIDR number actually means you have a larger network because it's not counting like how big the network is. It's counting how many bits are shared between all the IP addresses. So if you have less shared bits, you have more freedom to change them. So you have more possible addresses.
So does it only matter on like the local area level?
What do you mean?
So I mean, I'm not. I guess like I understand what it represents,
Right.
but I don't understand how and where it's used.
Right. So I think kind of, yeah. So it does only matter like for end devices. Usually you'd have the subnet configured, but also for routers, you do have to tell it like this subnet should be routed over to this location, basically. So you would tell it like take like everything on this section of the network and route it over to this other router, and then forward it there and then forward it there, something like that. Any other questions? All right. So these are some special IPv4 addresses. There's a lot more that aren't listed here because the slide would be like 3 times as long if we actually listed all of the special reserved ones. But these are the ones that are kind of important. So 0.0.0.0, this is basically just like a placeholder. Um, it's not considered a valid IP address. It's just like you use this whenever you don't want to actually put in an IP address somewhere. And it's also used if you have like a program or something listening for connections, you just use this to specify I'm fine with getting connections from any IP address. Then at the other end we have 255, 255. You can read it. It's the broadcast for the current network. So that basically just means remember earlier we mentioned where was it? Yeah, the last address in any network is the broadcast address, so you can send a packet there to have it sent to every computer on the network. So this broadcast address basically just means it's the broadcast for whatever network you're currently connected to. So no matter what your actual address is, you can just send something here and it'll be sent to every other computer on your network.
What's the number followed by the /4?
Oh, that's the CIDR thing. So it's just the shorter way of writing the subnet mask. So how big the network is. So the number after the slash is just how many 1 bits there are in the subnet mask. So we have the 127 range, which is /8, so it's huge. And that's loopback, so connects devices to themselves. So you might be familiar with 127.0.0.1. It's the first address in that range. That's usually alias to localhost on most machines. And that's like if you're running a server on your own computer, you connect to it by connecting to localhost, because that's the loopback address. But in theory, you can use the rest of the loopback addresses if for some reason you actually need to. And then next one, we have this 169.254, anything that starts with that. These are called link local addresses. And they're sort of weird. It's basically just a backup for when regular address assignment doesn't work. So if your computer ever gets an address in this range, that probably means something went very wrong.
That would be like, for example, if you connected, like if you just didn't have like any Wi-Fi, like no networking equipment, you just took a computer, used what's called like a crossover cable, just connected it to another computer, they would have a link local address because they're not on a network, but they can share information using those addresses because they're connected to each other, for example.
Yeah. But if you ever see that, like when you're connected to an actual network that's bad, it shouldn't be like that. So almost anytime you see that, it just means something's gone wrong. And then there's the 224 addresses are called multicast. This is basically a feature in IP where you can have multiple people subscribe to something, and then you can send out a packet and it goes to everyone who subscribed to it. It's kind of weird. It only works like for local area networks. You can't use it over the public internet. And it's not really used that often. And then everything after 240 is experimental. So those are just like, you're not allowed to use this for anything. And then there's also private addresses, which we'll go into in the next slide, and some other less important ones too. Does anyone have any questions? Yep.
Besides that, for example, if you take the broadcast address, what's where would the important part be which it actually determines which network you're on? These four numbers, are they at the end or are they in the?
So the broadcast address doesn't actually have any information about what network you're on. It's just like whatever router you're connected to should be able to figure it out, basically. So it's essentially like just you send something here to just say whatever network I'm currently connected to. Like if you're connected to RU Wireless and you send something here, then it should send it to every other device connected to RU Wireless. In practice, I don't think RU Wireless actually does that. A lot of networks have this disabled for sort of obvious reasons. Any other questions? Yep.
So there is like a broadcast on a network, not just local, like wide area on the internet. Yes, RU Wireless technically has a broadcast, they just disable it.
Right. Yeah.
You
Well,
could set packet or something that everyone.
yeah, exactly. And in theory, if they enabled it, you could do that from anywhere. If it was like if it was a public IP range, which we'll get into on the next slide.
A lot of times that's disabled because it can cause a lot of network congestion. So for example, like I think our protocol, I think uses the broadcast address to kind of like find like basically when you're first joining a network and you have to like first connected to something, you have to find somebody's it's called a routing table where you connect the IP address to the MAC address. So from the internet layer down to the physical or the data link layer. If like everybody on RE Wireless, like imagine like when your like device first comes on and first connects to the internet, it has to like use that protocol to then get something. People's devices would be broadcasting stuff all over the place. And even though RE Wireless is kind of like subnetted so that when it would happen and also broadcast is disabled, if it were disabled, that would jam up the network and it would be very bad.
Yeah. Any other questions? All right. So private IP addresses is something we talked about earlier with how you can have two devices in different places that actually have the same IP address. So there are three ranges reserved for this. The one you've probably seen with your home router is 192.168. And then there's also two other ranges. So there's the 10.0.0/8, that's the huge one. And then there's 172.16. I think RU Wireless gives out addresses that are under 172.16. So if you check the IP address on your computer or your phone or whatever, it'll probably have one of those. Um, and there's also stuff on the Rutgers network that starts with 10, but I don't think Rutgers uses the 192.168 one at all. So anyway, this is given to devices to communicate over local networks. And this is necessary because there aren't enough public IP addresses to cover every device on the internet. Um, so to actually access the public internet, we can't have two devices with the same IP address on the public internet. That would break everything. So you need something called network address translation, or NAT, which is done usually by your router, although you can technically get it. Actually, I have to plug in my laptop. Okay, crisis averted. Yep.
I have a question about how NAT relates to NAT type.
Relates to what?
NAT type, like open, moderate, strict.
I don't actually know what that is.
Okay, well, for example, like on a gaming console, right?
Right.
You'll have a NAT type.
Oh, okay, I
So
see.
like, if you have open, if your NAT type is open, like you can play the game normally. If it's strict or moderate, you wouldn't be able to like play with certain people. And if it's I guess closed, like you're not able to play online.
Right. Yeah, I think that's referring to plug and play, which is how a lot of games allow you to like directly connect to another person's network. So it's basically a feature that some routers have where you're allowed to request a port be opened for you so that people can connect to your computer through your router, basically. So some routers support that, some routers don't. Like on on the Rutgers network, so not just RU Wireless, but also like if you live in the dorms and you're on ResNet, there's they have plug and play blocked by default. You actually have to like contact OIT specifically to have it enabled if you have like a switch or something. I think there's an article about that on the OIT help website somewhere. Um,
So plug and play is not related to NAT.
It is related. It's basically like I should finish saying what NAT is
Okay,
first,
okay,
but so basically NAT is where you have a single public address for that applies to your router, and then your router keeps track of whatever connections you have open. So whenever you send a message out, your router will relabel it with its public IP address, and then it will also keep track of saying like, okay, there's a connection going out from this computer on my local network to this computer on the outside internet. And then when it gets a response back, it will remember that you sent out this request and it'll send it back. So this means that if it just gets an incoming request with no other context, it usually has no idea where to send it, which sort of doubles as a security feature because it means that nothing on the inside is reachable by default. But also for games, that kind of gets in the way because you want to be able to set up a connection with another person's console directly for speed purposes. So that's what plug and play is for. It basically just says like, listen on this port for anyone who tries to connect, and if they connect, send the packet to me.
Okay. And you just mentioned it. I had a question about ports. Like, what exactly is a port?
Yeah, that's something we'll get to in a couple slides.
Okay.
It's like plug and play related to like so the switch can't connect to like
Yeah, pretty much. Um,
like on the gas pipe, like
uh, that's a separate thing. I think those are called captive portals, and they're basically like that's unrelated. It's a thing that some Wi-Fi networks can do to make you connect. But I'm sure that McDonald's probably also has plug and play disabled. It's like pretty much any public network is going to have it disabled because they don't want people opening up ports on their public network. Any other questions? All right. And then there's also some special IPv6 addresses, just mentioning it briefly. So these are mostly analogous to the IPv4 versions. So we have the double colon, which just means all zeros. It's the same thing as IPv4. It's just a placeholder. Um, and then we have double colon 1, which is just all zeros followed by a 1 is loopback. So unlike IPv4, they didn't reserve an entire block of like 2 to the 24 addresses for this. They just made one because no one's ever going to use more than one of them. Um, and there's also a link local block for IPv6, but it's not the same as IPv4 necessarily, just because IPv6 is so much bigger. In IPv4, the link local thing is basically just a backup if like getting a regular IP address fails, which is why if you see that 169 address, it's like almost always means that something went wrong. But for IPv6, there are just so many addresses that you can literally just randomly pick one, and chances are like no one has ever picked that address before. No one will ever pick that address again before the heat death of the universe, so it's probably fine. Uh, yeah, so using link local IP addresses for IPv6 is actually a lot more common. And then there's also multicast. And IPv6 has these things called unique local addresses, which are sort of like IPv4's private address range. But again, because there are so many IPv6 addresses, there's actually space for you to put like an identifier in here. So like every single organization or like house or literally whatever that uses a local address is supposed to generate their own identifier, and that basically makes sure that all of these local addresses are globally unique. So like in IPv4, pretty much everyone's router has 192.168.1.1. In IPv6, your router would have like its own address that's completely different from every other router, even just locally. Any questions about this? Yep.
Okay, so routing table, right? That's related to DHCP, right? Or is it no?
DHCP it's essentially a service that it's a type of server that typically your router, like in your home, normally your router is running it. That does automatic IP assignment on a local scale. The routing table, well, each device has its own routing table, and that basically just tells the device, oh, in order to send to this IP address, I have to use this MAC address. That's so similar, yeah.
And so when it comes to assigning an IPv6 address, is it the device that assigns it or the DHCP or whatever else?
So that's something we're going to get into next workshop. We're going to talk more about DHCP, but basically you can do either one because, again, IPv6 is so big, you can literally just randomly pick one, and it's probably fine. But also there's methods where you like generate an IPv6 address based on your MAC address, because MAC addresses are like long enough that they're also globally unique, and they're in theory guaranteed to be globally unique by the IEEE.
Great question.
Yep. Any other questions? All right. So this is just a small note about networking equipment. We need devices between computers to forward messages. So switches forward layer 2 messages and routers forward layer 3 messages. This is basically just like the terminology for what they're called. And just a small note, most home routers do a lot more than just the job of a router basically, because people don't want to buy like 4 separate devices to access the internet. Um, so most routers have like a router in them, but they also have a built-in switch and a wireless access point, and a lot of modern ones also have a modem in them. So they're doing like a lot more than what we mean when we say router.
Okay.
Yep.
What's the difference between a router and a modem?
Right. So a modem is just like a physical translator. So it translates between like the cable signal you get into your house and an Ethernet signal that the rest of your computers use.
Oh, okay.
So the modem isn't really doing too much interesting from like the networking perspective. It's sort of just like an adapter, but it's a really fancy adapter because coax signals are like very different from Ethernet signals, so it needs to be pretty big. Any other questions? All right, so this is an important note because someone I think asked earlier, what's the difference between MAC addresses and IP addresses? So you might notice like the jobs of layer 2 and layer 3 seem very similar. They're both here to essentially like transport stuff from one computer to another. They both have their own kind of addresses. So layer 2 has MAC addresses and layer 3 has IP addresses. So it seems like they're basically the same kind of protocol, and in some ways they are. But the important difference is that layer 2 is transparent and layer 3 is not. So that basically means that for layer 2, nothing on the network needs to be aware of like anything that's happening at layer 2. So like every MAC address is basically just like pre-programmed into the device. It never has to change. It never has to like check what the MAC address is. um, so if you know the MAC address of another device, you can just send them a message over layer 2 and it'll work fine. And also importantly, switches are like hidden from devices. So you can't tell if I'm sending a message if I'm like directly connected to another computer over layer 2 or if I'm sending it through like 15 switches. It's completely invisible. And on the other hand, layer 3 is not transparent. So layer 3 requires configuration. You have to have someone figure out like what IP range do I want to use for this network? What IP address do I give each computer? Um, Stuff like that. And you also have to be aware of like where your router is. So your computer needs to know like this is my router's IP address. This is where I send all my packets to, and stuff like that. So in practice, you probably never experienced much layer 3 configuration because you have protocols like DHCP that manage it all automatically for you. Um, but the point is layer 3 configuration is still happening. And especially for stuff like DHCP, there needs to be a layer underneath that you can send messages to because otherwise you'd have no way to get that configuration done. And also, we can't all just use layer 2 because layer 2 networks have limitations. So, for example, you can't have a loop in your network, which is basically just like you have one device that's connected to another device that's connected to another device and it goes back to the first. So, you do ideally you want to be able to have those kinds of loops because it's good for redundancy. If one of them fails, then you can start routing stuff through the other loop or the other part of the loop. But with layer 2, you can't have that. Um, I think actually you can have it just as a fallback, but you can't have it like if we're getting a lot of traffic, we want to split it up between two different routers. You can't do that with layer 2 at all. Yep.
So layer two is for switches, and layer three is for routers.
Right. Does that make sense? Any other questions? All right. Um, so this is a small slide now about terminology. Technically, when you say packets, that just refers to layer 3 messages. And we have another word called frames that refers to layer 2 messages. So this is just good to know because you'll see the term frame sometimes. It's good to know what that's referring to. But people don't really strictly follow it. People refer to Ethernet or Wi-Fi frames as packets all the time. Um, it's just kind of a technicality. So a really important thing with all of these protocols that we've gone over so far, so link layer protocols and IP, is that none of these actually guarantee that messages will be delivered, and they might also arrive out of order. There's this term called best effort delivery, which means they'll try their best, but they can't make any guarantees. So in practice, usually you don't have that many packets getting dropped, but it does happen occasionally. If you send enough data, eventually like one or two of them are going to drop. So this allows some flexibility because some applications aren't going to care if a couple packets get dropped. Like, for example, a video chat, you're not really going to notice if like one frame of your video chat is missing, or like for a high quality video chat, one packet might even be just a few pixels, and you're not really going to notice that difference. So having like a live, up to date video stream is a lot more important than like a handful of pixels that might be missing or corrupted a little bit.
Another thing too is a lot of the like these protocols in particular, they have what are called checksums, which are they're it's redundancy that's put in place in the protocol. So like for example, even if let's say a bit gets flipped in a message or Well, if an entire message is lost, there's not much they can do about that. But for example, if something gets messed up in the message, they have ways to correct for that. And then once, I don't know if we cover the layer 4, so transport control protocol.
Yeah, we do cover it.
And that kind of takes care of this. So its job is to kind of manage where stuff is getting delivered and if it gets delivered.
Yeah, that's the next slide basically. So
I call it.
yeah. So the next layer up is the transport layer. Does anyone have any questions about that, by the way? All right. So the transport layer, the main thing it adds upon the previous layer are ports. So every device has a lot of programs running. So if a device gets an IP packet, it needs to know like what program is this actually for. So as a solution, every device or every program on a device can ask for a port, and the port is literally just a number to listen on. So for example, if you're running a web server, it will usually listen on port 80 or 443 for HTTPS. But either way, it's basically just saying to the operating system, if you get any packets that say they're for this port, just send them to this program. So the transport layer protocols include source and destination ports in their messages. And the main idea is that the network layer is sort of for connecting devices together, and the transport layer is for connecting individual programs together. So for example, like connecting your browser to the web server running on Chrome's supercomputers, or not Chrome, Google's supercomputers. Any questions about this? All right. So the simpler one is called UDP, which stands for User Datagram Protocol. And this adds like very, very little on top of IP. It just adds ports, which are the sort of fundamental feature of this layer, and a very basic checksum. So this checksum can't actually do error correction, which is what Harris was mentioning. It just tells you like, is this packet corrupt or not? So it's useful for applications like video calls that we mentioned, that you want them to be extremely fast, and also you don't really care that much if they drop packets every now and then. So it's also nicknamed Unreliable Datagram Protocol because it's unreliable. It can drop packets if you aren't careful. On the other end of the spectrum is TCP, which stands for Transmission Control Protocol. So this is the opposite of UDP. It adds a lot to the internet protocol. So TCP establishes a session between two devices, and applications using TCP don't see individual packets. They see continuous streams of data. So TCP guarantees that these streams will be transmitted reliably and that they'll always be transmitted in order. This is accomplished by having the receiver acknowledge everything that gets sent by the sender. So basically, like when you get a TCP packet, you're supposed to send an acknowledgement saying, I got it. And if you don't send that acknowledgement, the sender assumes that you didn't get it, and it will keep sending it again until you acknowledge it. So the cost is that this is slower than UDP.
So which type of softwares use TCP over kind of video conferencing?
Yeah. So pretty much everything uses TCP actually. So for example, like web browsing, HTTP goes over TCP most of the time, which is something we'll get to in a second. But pretty much all web traffic goes over TCP. Um, a lot of other stuff too, like
So the question is
Yep.
what usually goes under UDP?
yeah, the question, that's really the question, what usually goes under UDP. So there's video conferencing, which is like the best example. Also, I think voice calls, I guess, probably go over UDP. Some video games use UDP when they really need performance because you want to lower latency as much as possible. But also for video games, you do care about stuff getting received because you don't want someone to like make a move or like something like that and it just not get received on the other player's end. That would be really bad. So some games do use TCP, like Minecraft uses TCP for everything. Other games probably do too. Does that answer your question? Yeah. Any other questions? All right.
Oh, okay.
Yep.
So when you send a packet to a router, for example, right?
Right.
How does it know what? Okay, how does it know what port to go to?
So, yeah.
Sure. So if the router is just operating at layer 3, so at the network layer, the port, I'm not going to say it doesn't matter, but it's not used in that, in the routing and like sending of the information. Um, Typically from layer 1, so the physical layer, to layer 3, which is the network layer, that's concerned with actually where the packet is going physically. So normally that's between computers, between network devices. Once you hit layer 4 and above, typically that's within a machine. So that's when their machine will start like basically unwrapping the packet, unwrapping the data. So in that case, like once, let's say a packet gets to your machine, it's already gone through layer 1 through layer 3, physical layer, data link layer, network layer. It's gone to your machine. Then TCP or UDP can then read that packet and then say, oh, this goes to this port 80, web traffic. I'm going to send it to the web browser. Then the web browser can go and read, for example, the HTTP data. So in terms of actual network operation, so like actually like kind of routing and getting the packet to where it needs to go, layer 4 and above isn't really used for that. It's mostly just used to get it like to the right spot within the machine itself.
Yeah. It is worth mentioning that also for NAT, it actually does have to be used because you could have two devices on your local network that are listening on the same port, and then your router would have to assign them different ports, and it has to like change the ports up when it uh, forwards the packets, basically. So it is used on that, but outside of that, it's not really used for routers.
Port forwarding.
Yeah, and then port forwarding is sort of like the other way around. Or port forwarding is basically like UPN or plug and play, but you set it manually. Any other questions?
So
Yep.
when before my packet leaves my system, does it need to know what port it's going to go to on? Okay.
Yeah. So it'll have a destination port in the packet, and then when it gets to the server on the other end, it'll read the destination. All right. So this is sort of a transport layer protocol. It's a much newer one called QUIC. It technically stands for Quick UDP Internet Connections, but I don't think anyone actually uses that as an acronym. So this is actually implemented on top of UDP because by the time the idea for this came around, it was like too late to add another transport layer protocol because like all of the home routers and stuff have already been like basically built around there only being two. Um, and it's like TCP but with way more features. So it has built-in encryption, has a faster setup time, so there's less latency for loading. There's multiplex connections, so you can have like multiple streams of data going over a single connection. And there's much more stuff. And it was developed by Google alongside HTTP version 3. So I think it's currently has support in Chrome. I don't know if you have to enable like experimental features for it to work, but it's like a little over 10 years old at this point, and it's still sort of being very gradually rolled out. Um, so it's basically designed around like solving the problems that would not have existed back in the 90s. So like problems that you experience with the modern internet, stuff like that. It was basically developed specifically for web browsing. Any questions about this? All right. And then finally, the last layer is the application layer. There are a ton of protocols here. This includes HTTP, which we've been using as an example. There's also protocols like SSH, which you use to connect to a shell on a remote machine. And then there's FTP, which is the file transfer protocol. Other protocols, and then custom ones like video games, like Minecraft has its own protocol. Every single game probably has its own protocol. And this is the highest level there is. So we only have to worry about the contents of the message at this point. We don't have to worry about how it gets there at all. Yeah. Okay. This is the.
Oh, So
Yeah.
they're gonna be very good. I got this slide.
All right. That's all, everyone. So thanks for coming.
Thank you guys.
Any final questions? Yeah.
Oh, okay.
Yeah, pretty much.
Good call.
Yep.
Thank you. Let me work myself in.
Yep.
Just have a few questions.
Sure.
I'm new to this club.
Uh-huh.
I have like a little experience with like networking.